All right, hello, welcome everyone. We are so glad to have you joining us today. My name is Kate Neff, and I am your host here at the Denver Museum of Nature and Science for today's program, Scientists in Action, Virtual Voyage Through the Universe. Thank you for giving us part of your afternoon or your morning, wherever you are. We have folks joining us from Alaska, from Tennessee, from California, from Wyoming, and of course here in Colorado, probably other couple states that I've even forgotten, and we are just so thrilled to have you joining us. Before I introduce our scientist in a matter of minutes, I just want to go ahead and touch base on some housekeeping items. If you are on camera school, I know we already got to do our tech check, but we're going to make sure that you're off camera and muted until we're ready for the Q&A about halfway through the program. If you are not on camera and you have questions, love it. We still want to hear them. We have a chat open and we're going to have you type either students on one-to-one computing or maybe teachers on behalf of your students into that chat so that we can also get those questions passed along to our scientist. Speaking of which, without further ado, I would love to introduce one of our curators of space science, our beloved astronomer, Dr. Chun Yu. Chun, what can you tell us about being an astronomer here at a museum, and what is this amazing software that's taking us into outer space today?
Thank you, Kate, for that wonderful introduction. As Kate says, my name is Chun, and I'm an astronomer at the Denver Museum of Nature and Science. And astronomers basically study the universe. So they can study stars, they can study whole galaxies, and there are even astronomers who study the entire universe, known as cosmologists. And astronomers use a lot of different tools to study the universe. And the primary one is a telescope. And before we get to a telescope, there was a pre-video that many of the students out there might have had the chance to watch. And if you did, there was a request to do an activity. So unfortunately, I can only see one classroom, but if there are any students in that classroom that did the activity, feel free to raise your hands so that I can see them. I don't know if anyone's raising their hands. I don't see anyone yet. And if you did the activity, and you're on chat, feel free to put that in the chat. There might have been one or two students. And basically, the activity was to do what all good scientists do, which is to go out and observe. And right now you can see this planetarium software that we're using, that I'm controlling, and we'll be seeing that throughout the entire program. But Kate, I believe we do have some pictures that were sent back from students who were able to do this observation.
We do.
And yes, and these are great pictures. What I asked students to do was to go outside early in the evening and look for the Big Dipper. And so here are a couple of drawings and of the Big Dipper. And then a couple of hours later in the evening, they're again supposed to go outside and draw the Big Dipper again and see whether it had changed position or moved. And so on the picture on the left, you can see the Big Dipper over the horizon, what looks like the horizon. And on the right, you also see two different pictures of the Big Dipper with maybe a tree and a lamppost in the foreground. And these students are doing exactly what a scientist would do. When scientists go out into nature, or whether they're in a lab doing an experiment, they are observing very carefully. And they're recording their observations, whether you're drawing or writing down in your notebook or making cataloging information in a computer. You're doing exactly what a scientist would do. And then when I'm presenting to this, you're also spreading the information to other scientists and to other people, which is also super important. Now, astronomers, in addition to looking out for themselves with their eyes, usually astronomers don't just use their eyes, but they use telescopes. And so here is an example of two telescopes. There's one obvious one in the foreground on the right side. That's a telescope that an amateur astronomer, a non-professional astronomer might use. And you might know someone who has a telescope like this that you can look at planets or the stars with. And then off in the background towards the left, there's a dome building and there's a telescope inside that. So that's a big professional telescope for astronomer scientists. And we can also put telescopes in orbit. And so we have a picture of the Hubble Space Telescope coming up, and putting them in orbit puts them above the atmosphere, which can blur images. The air in our atmosphere can also block certain wavelengths of light. And so astronomers use telescopes on the ground, in space, they use cameras and other instruments on spacecraft, on rovers, all to collect an enormous amount of information about our known universe. And what we're presenting today in this tour of the universe is planetarium software that shows a lot of these data sets. And so every visualization that you've seen here we're seeing the Earth is based on, all this is based on real data. So none of it is fake. And this is all as scientifically accurate as we can make it. And so with that introduction out of the way, what you're going to have an opportunity to do is to drive this presentation. So we actually have several polls, and the first one will help us decide which rocky planet do we want to visit first. Do we want to travel to Mercury or Venus or Earth or Mars? So for teachers, feel free to poll your students and enter it into the poll feature on Zoom. If you're on a computer yourself, you can also access the poll yourself. And we'll probably give maybe another 10 or 15 seconds, right, Kate?
Yep, sounds about right. And if you're unable to use the poll for any reason, you can post it in the chat. So go ahead and take a couple more seconds. All right. Wow, we're seeing a trend. No love for Earth. No one wants to see Earth. We're already here, I guess. But unsurprisingly, we are most interested in visiting Mars. So how long would it take us to get to Mars if we were to go ourselves, Kajun?
All right, well, it would actually take many, many months. So we're going to go there in seconds because we're in a simulation and we can travel much faster than the speed of light. But for astronauts or spacecraft that we send to Mars, those trips have to be done when the planets are aligned just right, because that takes the least amount of energy. And even when that's the case, it can take anywhere from 6 to 9 months to get to Mars. And it takes about 26 months for the launch window to appear, for the planets to be aligned just so. And so if you miss your window, that means you have to wait another 2 years to get to Mars. But as you see, we got here in seconds. And the two circular lines are the orbits for Mars's 2 moons. So whereas planet Earth only has 1 moon, which we imaginatively call the moon, Mars has 2. And when we start visiting the other planets, you'll see that there are many more moons in the solar system. So as we plunge down to the surface of Mars, we can see why it's called a red planet. It's pretty uniformly sort of reddish in color, although they're different, they're lighter and darker tones. Unlike Earth, which has the white of the clouds and the blue of oceans and the greens and browns of the continents, Mars is pretty monochromatic. And you can see that there's one very distinctive feature that is all over the surface of Mars, and these circles are craters. These are caused by impacts from asteroids or comets colliding with Mars, and they explode and carve out these big round dimples in the ground that we call craters. And if we wander around just a little bit more, let's see if I can find some of these features, you'll even see that Mars actually has features that look like they were eroded or carved by water. If you look down here, if you've ever played in a mud pit in your backyard with a hose running, you might recognize how the mud or the dirt is shaped by running water. And so here are features that might have been carved by running water more than 3 billion years ago. And we see evidence of this in our photography from spacecraft looking down. We also see chemical evidence for water in the rocks that we are sampling with our robotic explorers on the surface. So Mars was probably wetter and warmer in the past, but over the last 3.5 billion years, it's lost most of that water, and it's also lost even most of the air in its atmosphere. So currently, Mars's atmosphere is only about 1% the thickness of the Earth's atmosphere, and it's mostly carbon dioxide, so it's really unbreathable by any animals like us humans. All right, while we're still at Mars, are there any questions in the chat or Are there questions? Do we want to go to other questions from the classroom, Kate?
I think while we're waiting for questions in the chat, one thing I'll go ahead and just pose because I think everyone's probably thinking about it. Could we survive on Mars? Could we grow plants there? What would it take for humans to live on Mars?
Well, if you think about what it takes humans to survive, we need air, we need water, and we need food. So unfortunately, all three of those are in pretty short supply on Mars. Like I said, the air is pretty thin on Mars, and it's mostly carbon dioxide. So you would have to bring your own air for those first missions. We think there is buried water in the form of ice that could be deep beneath the surface, but you would have to mine that water, and then you'd have to have the energy to melt it and to filter it to extract the water. And then finally, you would, for the most part, have to bring your own food. So like I said, it could take 6 months to travel to Mars, a year on the surface to wait for the planets to line up again for an efficient trip back home, and then at least another 6 months to travel back to Earth. So that means a mission to Mars is at a minimum on the order of about 2 years long. So that means quite a lot of food. So if you were to grow food on Mars, you would have to bring all of your growing supplies, seeds, and plants, and greenhouses, things like that. So for astronauts going to Mars for the first time, it would take a lot of materials and supplies and a lot of efforts and new technologies that would have to be created to help us survive on Mars.
As far as excuse me, as far as like weather and stuff is concerned, how hot does it get on Mars? Do they have seasons?
Yeah, so Mars, because it's tilted on its axis like the Earth is, it actually has very similar seasons to Earth. So it has summer, winter, spring, and fall. But because Mars is about 50% further from the sun, and the atmosphere is so thin, even though it's mostly carbon dioxide, and you might remember that carbon dioxide traps heat in our atmosphere, very little heat is trapped on Mars. And so it does get very, very cold. Now, on a warm summer day, perhaps at the bottom of a valley, you might get up to 40, 50, 60 degrees. But for the most part, you should think of Mars as at the warmest, typically like being in Antarctica here on Earth. And at its coldest, it's much, much colder than on Antarctica. One thing that Mars does have is it does have dust storms. And so even though it has a thin atmosphere, it can pick up dust, and it can have dust storms that can trap the surface under this cloud of dust for months at a time. So Mars is very, very different from the Earth.
It looks like our audience is really interested in maybe comparing some of Earth to Mars. Could you maybe speak to, for example, like the indentations that we're seeing, the craters? Like, why does Mars have this, but Earth doesn't? Why does Earth still have so much water and maybe Mars doesn't? How much water did they have in the past? What does that kind of look like when we compare the two planets?
Yeah, so those are all great questions. And let's see if I can answer all of them without having you to repeat the question, Kate. But as you see, and as I've mentioned before, Mars looks very different, mostly because of the craters. Mars does have some volcanoes. There's actually 3 volcanoes in a line. There we go. And the 4th one just poking through up in the top left. But the reason why Mars has so many craters is because it has such a thin atmosphere. So, and it doesn't have any running water anymore on the surface. So Earth is bombarded by asteroids and comets just as much, if not more so, just because Earth is a larger body. So there's more of Earth to Earth's surface to collect impacts. But there isn't the same sort of erosional forces on Mars as there is on Earth. So on Earth, we have running water, we have weather, we have wind. All those act to erase craters over time. So after a few thousand years, craters tend to disappear from the landscape. But you don't really see that on Mars. Even the thin atmosphere, I talked about the dust storms just tend to move dust around. There really isn't enough dust to cover or fill in the craters. And as far as how Mars became so different from the Earth, like I said, we think both planets probably Mars was warmer and wetter, and in some ways Mars was more Earth-like in the past. But Mars has one crucial difference that's different from the Earth, and that is Mars is smaller than the Earth. So it's only about half the size of the Earth if you in mass. And if you were to go onto the surface, you would weigh about 37% of what you would weigh here on the Earth. So the gravity would be less. But because it's smaller, it lost its internal heat sooner. It doesn't have a magnetic field because you need a liquid iron core to drive a magnetic field. And that magnetic field protects Earth's atmosphere. On Mars, there's nothing to protect the atmosphere from the solar wind and from cosmic ray particles. And so over time, Mars lost its atmosphere, it lost its water all into space. It all basically dribbled out into space. And until what you see now, it's basically a very cold, very desolate, and very dry place because it's lost most of its water.
Wow, kind of beautiful and also a little sad.
Yes.
Just a lesson of impermanence, nothing stays the same, even in space. So just to kind of summarize it, it looks like, because I'm seeing a common kind of couple of questions throughout the chat, it looks like Mars, probably had water in the past, doesn't have it liquid in the present. Maybe life could have existed in the past, probably not likely now, because even a plant probably wouldn't do so well. So it might be nice to explore Mars in our future, but for now it's sounding very cold and dry. Would you like to take us to another planet, Kachun?
Yes, I think we're ready for our next poll. So we were focused on the inner planets, those inner rocky worlds that have thin or no atmospheres. And now we're going to look at the giant planets that are mostly gases. So lots of atmosphere. So we can pick between Jupiter, Saturn, Uranus, or Neptune.
All right, so students, teachers, go ahead and place your vote. Who are we going to see next on our amazing intergalactic tour? All right, we're going to give it about one more second. We have a tie. Anyone in the chat has a vote? All right. Well, we're still at a tie. Kajun, you are gonna have to make a choice, or you're gonna have to take us to both, because we are interested in both Jupiter and Saturn.
All right. Well, I think I'm happy to try and go to both. I think both of them are wonderful planets. And so let's go to Jupiter, kind of the king of the planets, because it's the largest in the solar system. And as we fly to Jupiter, you'll see we're passing through all these orbits of Jupiter's moons. So Jupiter has actually 80 known moons. And a lot of the moons are in kind of these haphazard, kind of a mishmash of different orbits with different inclinations. And those are moons that are likely captured asteroids or comets. But you see that there are some moons that whose orbits line up with Jupiter's equator. And so these are moons that were likely formed with Jupiter. And we're going to fly past one of them right now. I'm not even sure which one that is. That could be Callisto. But as we fly down to Jupiter, you see why Jupiter is called a gas giant, because we're seeing the cloud tops on Jupiter. We're seeing the swirls of clouds and the weather patterns on Jupiter. If you watch the TV news, you know that when you watch the weather report, they will show Earth's weather as shown by weather satellites. And you'll often see the swirl of clouds and of storms. And the same sort of storms can appear on Jupiter, or very similar storms. And so let's see if we can get the storms, the planet rotating. And you can see how complicated the cloud patterns are. There are different horizontal bands, some lighter in color, some darker. On the bottom, you can actually see a shadow of a moon in orbit. That's what that dark spot is. But the storms on Jupiter show up as kind of these whitish ovals. You can see these circular features. Those are gigantic storms. You can think of them as hurricanes. And if we go a little bit faster, we'll probably start seeing the great red spot. Here we go. Here it's coming into view. And so this is a storm that's been observed for centuries from Earth, ever since astronomers were able to point at their telescope at Jupiter and see any much detail on its disk. The great red spot immediately showed up. And so this is a hurricane that's been going on for multiple centuries. And it's so big that you could drop the Earth right in there. So just like at a pool table, you can drop a billiard ball inside the hole in a pool table. You can think of the Earth as small enough to fall into that great red spot.
Wow, that's pretty wild. That's a big planet for sure.
It is.
Um, so here's a chat question, and I think this kind of relates to another common question. So these gas giants, are they gas all the way through? Is there something at their center? Because how do storms survive if there's no surface? Is a question that someone has asked.
Yeah, so that's a great question. And actually storms can survive easier in these gas giants than they would if there was a surface. We think Jupiter and Saturn, and let's just go ahead and fly to Saturn since that's coming up next. They do have rocky interiors, and so there is probably a multiple Earth mass core that's at the very center of these worlds, but you have to fly through thousands and thousands of miles of atmosphere to get to them. And by the time you get to the surface, you are, you're equivalent to pressures that are so great that they would probably crush your spacecraft. Now, on Earth, storms actually slow down once they hit land because the reason why storms form is because heat from the sun drives water in the oceans to evaporate. And that energy helps drive storms. And so once they go over land, friction from the land and the lack of water basically dissipates storms or makes them go away. So on planets like these gas giants, storms don't have a surface, and they are still driven from heat from the sun, as well as heat from their interiors. There's actually quite a lot of interior heat that's still bleeding out from these planets. And so it sort of makes sense that storms can go on for a long time. Now we're at Saturn, and we again flew past a bunch of moon orbits around Saturn. The most distinctive thing about Saturn are its rings. But since we're on the topic of storms, I'll point out that Saturn has far fewer storm-like patterns, or they might be smaller, and so it's not as vibrant or colorful or chaotic looking as Jupiter. And part of the reason is that Saturn is further away. So Jupiter is about 5 times further from the sun than planet Earth is, but Saturn is about 9.5 times, so almost 10 times further from the sun than we are. And as a result, it gets about 1% the amount of sunlight. So there's far less heat coming to Saturn and less energy to drive the storms. Now, from this view of Saturn, you can see that it looks like a break in the rings on the right, but what it is, it's Saturn's shadow cast on the rings. So the rings are still there, but the shadows cause the rings to look like they've disappeared. But if you look carefully, and this might be a little bit tricky to do, you might notice the stars blinking in and out. They don't completely disappear, but sometimes they get brighter and sometimes they get dimmer as they go between the rings. And so astronomers actually were able to measure this from Earth. They would watch the stars pass behind Saturn, and they would see the stars blink on and off. And that was a clue that told them that the rings are not a solid thing. They're actually made up of trillions of microscopic and small bits of ice in orbit around Saturn. So these rings are not solid. They're made up of ice that came probably from a moon, an icy moon that wandered too close to Saturn, and it broke apart in Saturn's gravity. So that is Saturn. And I think we're ready for either more questions from the chat or even questions from our school that's on camera.
Yeah, you answered funny at the end a number of questions that people are asking, like about how solid are these rings? Can you land on them? What are they made out of? So it sounds like no, you cannot land on them. They're made out of really teeny tiny ice particles, which have to be pretty cold. Do you know how cold it is, Kachun?
I don't know off the top of my head, but I mean, they're cold enough to freeze water, obviously, and maybe some other ices or gases as well.
Very cool. Well, one request I'm going to have is when we back out of Saturn, do you mind just showing the moon again? Someone did ask, what are all those things around Saturn? Those are moons, because Saturn has, I think we decided earlier, 83. Is that correct? Like 83.
Yeah, I think the current count is 83 moons. So there are 80 around Jupiter, 83 around Saturn. And if we turn on time again, we can actually see these moons. Let me go a little bit faster. So you can see the moons going in orbit around Saturn. So
Very
these lines do trace the orbital paths of the moons.
neat. All right. Well, thank you for sharing both of those planets with us. We're so lucky. At this point, we are going to invite Normandy Elementary School on screen. And I'm going to add you if you'd like to go ahead and unmute. We're going to have a question one at a time so that we can hear you nice and clear. But what questions do you have for Chun?
So hold on. So about Saturn, is that what we're asking a question about? Okay, what's your question?
The rocks that form the rings of Saturn do they at all crash into the actual planet Saturn?
Yeah, that's a really good question. So let's do the particles that make up Saturn's rings. Do they eventually fall in? And it turns out that there are processes that can alter the orbits of these ring particles. So you can think of the ring particles. There are a range of sizes. Most of them are pretty small, microscopic. They could be the size of a pebble or a small rock or maybe your fingernail. Some of them are microscopic in size. The largest particles might be the sizes of boulders or even cars, but those are pretty rare. But the smaller particles, not only are they in orbit around Saturn, so they orbit because of Saturn's gravity, but there are also there are pressures from the sun, so radiation pressures and other forces that can actually slowly cause these particles to spiral in to the planet. So we think that Saturn's rings are not permanent, meaning over time, if you wait hundreds and hundreds of millions of years, the rings will change their appearance. And then over time, they'll disappear entirely. So there's speculation, depending on the scientists you talk to, these rings might have been formed 500 million years ago. They might have been formed a billion years ago. But if you were to wait like another few hundred million years from now, you might see much fewer rings or less vibrant rings, or perhaps no rings at all. But that's a great question.
Very cool. That was an awesome question.
Feel free to give us your name too, before you ask your question.
Are they allowed to ask any question or just?
Yes, you can ask any question.
Yeah.
Okay. All right, I'm gonna have
Questions.
I'm gonna have Lily come up real quick. Lily, come on up. These are questions that you wrote down earlier. So Lily, ask your question.
What other planets have been discovered that could support life?
Okay, thanks for that question, Lily. So currently, we don't know of the existence of life anywhere else in the universe other than Earth. So let's go ahead and zoom out to show the rest of the solar system. We were on Mars, and let's see, somehow all the orbits disappeared. So let's see if we can turn on the orbits again. And like I said earlier, there is speculation that, or there's a lot of evidence that Mars was warmer and wetter. And here on Earth, anytime that we have seen or water here on Earth, we see life. And so there's speculation that perhaps Mars had life billions of years ago. And right now, Mars is a very harsh environment. And so it's very difficult for even bacterial life to survive on Mars. But if Mars had life billions of years ago, perhaps what bacterial life survived might still be surviving deep underneath the surface. So there could be warm reservoirs where water could exist and these bacteria could survive. And since then, in the last couple of decades, we've also been finding moons that have evidence of liquid water underneath them. So here's a moon called Europa that orbits Jupiter. And Europa is covered by a gigantic icy shell. And this is a shell of ice, water ice, and it could be 10 miles thick. So it's very hard to drill through it. But we think underneath this icy shell is a liquid ocean that could hold as much as 4 oceans worth of water, 4 Earth oceans worth of water. And again, if there's liquid water, what are the chances of life? We don't really know. We currently don't have spacecraft exploring Europa, and it's unlikely, at least for a few more decades, that we can send a lander to drill into the ice. And we've discovered lots of other moons with potential underground oceans. And we've also discovered more than 5,000 planets that are in orbit around other stars. And some of them are in what we call the habitable zone, meaning they orbit not too close and not too far from their sun, so that liquid water can exist on their surfaces. So whether they have life or not, that's still a question we haven't been able to answer yet, but scientists are definitely interested. So we'll just have to pay attention.
That was a
Thanks.
great question. Thank you, Lily.
Say your name.
I'm Parker, and how many solar systems do we know of that are in the universe?
Okay, that's a pretty amazing question. So we're gonna fly away from our solar system, and a solar system is defined to be a star with a bunch of planets around it, or with at least one planet. And what we're going to do is we're going to fly out so far that we're going to see the other stars start moving. So you can see we're flying past the nearby stars. And now we're going to see the entire Milky Way galaxy. So the Milky Way is just a gigantic conglomeration of stars, all held together by their collective gravity. And the sun is just one star in orbit around the Milky Way. So the sun is in orbit around that central bright part of the Milky Way. Now we're seeing the glow from the Milky Way because the glow is coming from hundreds of billions of stars. And like I said earlier, just a minute ago, we now have found more than 5,000 planets around other stars. And we only started looking in the past 25 years, so that hasn't been very long. And finding planets is actually very, very difficult. So we've had to develop a lot of new technologies. But there are estimates that most stars contain at least one or more planets. That means for every star, there's likely to be at least one planet. So there's likely to be a solar system for most every star in the universe. And in our galaxy, we think there's anywhere from 200 to 400 billion stars. And in the observable universe, there's probably on the order of 100 billion galaxies out there. So you can imagine that's a lot of galaxies if you multiply those numbers together. Thanks for that question, Parker.
Yeah.
Wow, that's a lot to wrap your brain around. Thanks, Parker.
I'm Hazel, and what would happen if the Earth got knocked out of place and started spinning the opposite direction?
Okay, wow, that's a crazy question. So let's jump back to our solar system. And one thing that I didn't turn on and show were all of the smaller objects in our solar system. So I've just turned on the asteroids. So that's what all these red dots are. And let me get time moving again so that we can see the asteroids moving. We might have to go a little bit faster. There you go. You can see all the asteroids orbiting, and you can see the planets in orbit around the solar system as well. And you can see the amount of material kind of peters out, but there's lots of also more icy bodies out there, out at what's called the Kuiper Belt. And there are actually probably billions of objects that are much smaller than the planets. So these include the asteroids, and they include comets and other bodies. But the total amount of matter in the asteroids and the comets are actually pretty small. If you added them all together, they might not be much bigger than the amount of mass in our moon, or maybe a few moons worth. They would definitely probably be smaller than the Earth. So there isn't enough matter in our solar system for something to collide with the Earth to knock it off course or to flip it around. And as you can see, most everything does orbit along in pretty much the same direction. There are some objects that quite don't orbit this way, but everything kind of orbits clockwise from this particular vantage point. And you can see that the planets are orbiting far away enough that they're not going to collide with each other. So it would be, we do expect Earth to get eventually be hit by objects coming from space, and some of them can be very destructive, but it is very, very unlikely for anything in our solar system to hit the Earth hard enough that it could knock it out of its orbit or to alter its spin or to flip it around. Although I guess you can imagine if something coming from outside the solar system was big enough and going fast enough, that could happen, but that would also be highly, highly unlikely. But thanks for that question, Hazel. That's really thinking out of the box.
Thank you.
My name is Caden. What is the largest singularity that's been discovered in a black hole?
Okay, so that's a pretty deep question as well. So black holes are these massive bodies that have collapsed. They've either collapsed from stars or from other objects. And we often think of black holes as sort of being like vacuum cleaners in space, but that's actually not a really correct description. If the sun was to turn into a black hole magically, because there's no reason for the sun to, and it's impossible, but the black hole would have still the same amount of matter as what's currently in the sun, and it would have the same amount of gravity. And what that means is that the planets in orbit around the sun now, and if you were to suddenly blink the sun into a black hole, the planets would continue to orbit the black hole sun, and nothing would change, other than the fact that we would no longer get any light or heat from the sun. But we do find black holes at the centers of other galaxies. And our Milky Way has a black hole, a supermassive black hole, that's about 4 million times the mass of our sun. And I'm not an expert on black holes inside other galaxies, but I think the largest black holes that have been discovered so far are on the order of like 10 billion solar masses, so 10 billion times the mass of our sun. So these are pretty enormous, gigantic black holes as far as mass. But even still, I mean, they don't actually take up that much space. So a black hole, I think in our galaxy, that supermassive one might just fill up our solar system. And there's a lot of space between our solar system and the nearest star. But that's a great question.
Thank you.
Okay, do we want to continue with questions from Normandy, or do we want to take some questions from the chat? How do you want to do this?
I'd say we have time for at least one or so more questions from Normandy. Okay. It's nice because a lot of these questions that people are asking in the chat, you're actually already addressing. So
okay, terrific. That makes it easy.
Yeah. So
okay, my name's Tate, and how long can Earth sustain itself before it may die?
Okay, well, the way that Earth sustains itself, wow, these are all really deep philosophical questions. I love it. But Earth, sustains life because it has an atmosphere and it has light and heat from the sun. And we know that the sun is about midway through its life. So the sun, the solar system, all the planets are about 4.5 billion years old. And it has another 4.5 billion more years before the sun dies. And so it's going to be a long time, much longer than anyone that you could possibly know, or even our far off ancestors. Humans, Homo sapiens, the human species, has been on Earth for only 200,000 years. So to think about another 4 billion years of life on Earth means that it's going to be a long time before Earth is completely uninhabitable because the sun has died. But there are, probably some other things that that might affect life. We know that the Earth could get hit by an asteroid. At some point, the Earth has been pummeled by asteroids and comets over its past 4.5 billion years of history. So it will continue to do so. And as a result, NASA and scientists are interested in tracking and finding every single object that could potentially harm us here on Earth. And we find them we will know whether we're in danger of any one of them, and we can plan accordingly by sending spacecraft to try and divert them, for instance. So the fact that we understand space and our solar system really well means that we can actually protect our planet from the hazards of space. But thanks for that question, Tate. So Kate, do we want to continue with questions, or do we want to go to our next and final poll?
You know, I think I do see a friend who's stepped up to the mic a couple times. Do you want to go ahead and ask your question? And we'll make this our last question from Normandy. And then we'll kind of turn it back to the chat. What question do you have, my friend?
My name is Tyler, and my question is, how did the planets make themselves?
Yeah, so that's a great question. So let's zoom back out to look at our solar system, and I'll turn the asteroids back on, and we'll kind of center ourselves on the sun. And you'll notice that all of the planets, along with the asteroids and the comets and everything else in the solar system, look like they all line up. So notice all these orbits are very close to each other in space. And here I'm going way too fast, so let's zoom back in. And if you were to build a scale model of the solar system, you could probably fit them into a pizza box because everything is relatively flat. And this is actually a clue to the origins of our solar system. And other clues come from looking out of our solar system at young stars out in our galaxy. But what we think happened is a cloud of gas and dust collapsed due to gravity, and that gas collapsed into the sun to form our star, our main star, but then the remainder of the gas piled up into an accretion disk. And so you can imagine a disk of gas and dust that's sort of like a frisbee or a pancake surrounding the sun. And then over time, gravity drew the gas and the particles in to form the planets. And there are still some remaining objects that weren't collected into the planets, but for the most part, the planets grew out of, or they accreted from the material that was in this disk. And you get a hint of what that disk looks like from the remaining asteroids and comets that still orbit the sun. So that's the leftover matter, stuff that never accreted or fell onto a planet.
Thank you.
So thanks for that question.
Awesome. Well, thank you so much for those amazing questions. I wish, like I said, that we had just all the time to talk about all the space, because I know I'm learning a ton. Kachun, do you want to go ahead and just take us to one last location in our last kind of remaining minutes? And we'll throw a poll up really quick so that y'all can help guide us, but we have probably time to do one more quick visit of something else that is not a planet. We can either see the Milky Way, which I guess we kind of already did, another galaxy, a star nursery where stars are born, or maybe a star graveyard where they go to die. I don't know. What does that look like? Go ahead and cast your vote, and Kachun will hopefully take us there.
And there's a lot more to learn about our Milky Way galaxy too, so definitely feel free to check that if you're really interested in our Milky Way.
All right, looks like star graveyard is going to be kind of the people's choice.
All right, well, that's a wonderful choice. We've been looking at our sun, which is kind of a medium-sized star. So there are stars that are much larger than our sun, actually 100 times more massive than our sun. And there are also stars that are a lot smaller, almost less than 10% the size of our sun. But all stars eventually die, and when they die, the reason they die is they run out of fuel. So stars like our sun and all stars burn hydrogen, and I call it burning, even though what that really means are nuclear reactions. Hydrogen fuses into helium, and the helium can also fuse into larger, heavier elements. But after a certain amount of time, depending on how big the star is and how quickly it uses its fuel, the star has no more fuel left, and it collapses, and it can also blow away its outer envelope of gas. So I think we have a picture of one example of this captured by the Hubble Space Telescope of a star that has ended its life. And so the remnant of the star is still in the center. It's something called a white dwarf. So the core of the star has collapsed into an object that's about the size of the Earth, so 100 times smaller. And this is probably what our sun will turn into at the end of its life in about 4.5 billion years. But the outer shells of gas that expand out from the star are then ionized or lit up by that central white dwarf. And so you see these kind of beautiful, almost butterfly or squid-like patterns of gas that's been expelled out from the star, and it's being lit up by the ultraviolet radiation from that central star. So this is what happens to relatively small stars or medium-sized stars like our sun. They're not the most massive stars. Now, if you're looking at stars that are at least 8 times the mass of our sun, they have a much more explosive end. So instead of having a gentle blowout of the outer envelope, they have this catastrophic explosion, something called a supernova, where the amount of light that's put out can outshine an entire galaxy. And this is a picture from, again, of Hubble, from the Hubble Space Telescope, of the Crab Nebula. This is a star that went supernova and was recorded by Chinese astronomers about 1,000 years ago, just under 1,000 years ago. And you can see a hint of how violent it was, because you can see the chaos of all the gases that have been expelled out. There's just ribbons of gas, and it just looks very messy. And at the center is a neutron star, and that's something that's very compact. It's about 10 kilometers across, so much, much smaller than the Earth. And the radiation from that star is also lighting up these gases. So these are kind of the two possible end states to stars when they die. And what's kind of neat about this is that the gas that's thrown out basically gets recycled. It can end up in a future star. So this gas doesn't go to waste. It can end up in a cluster like this, where the cloud, you can see the clouds along the edges. So we're looking at a stellar nursery, a place where stars are being born. So you're getting 2 places for the price of 1 pole. But you can see lots of stars clustered in the center and out along the edges. And those are thousands and thousands of stars that were born out of this gas cloud. So once these gas clouds collect, the gravity in these gas clouds can cause parts of the cloud to collapse into stars, into new stars. And then you have a new generation of stars forming. So with that, I think we've run out of time. Is that right, Kate?
Yeah, we are sadly out of time. What an amazing, thing to end on, though. Kind of tragic and devastating, but also beautiful because, like we said, everything's impermanent and space is incredible. If you have questions and you didn't get them answered today, we are so sad. We have so many questions as well, always. Please look those up. Let us know what you find. Share with each other. Science is about sharing, and just being curious and learning new things. Chun, anything you want to link the students on today as far as how do they pursue something like this in the future?
Yeah, so hopefully, you've learned a lot about space and our universe, and you've also learned how much there is out there. There's a huge variety of things in our solar system, as well as outside of our solar system. And hopefully that has inspired you to learn more, whether it's in your classroom or by yourself at home at the library or on the internet. And perhaps one of you will be a future scientist who will help us uncover some other mystery of the universe, or perhaps you could be an astronaut who's the first one to walk on Mars in the future.
That would be
great
so
things to
cool.
think about.
Yeah, definitely. And if you become an astronaut, please think of us. Remember, come say hi. Thank you for our on-camera school. Thank you for our chat questions. Thank you, Chun, for giving us your time. Thank you, Asa in studio. We couldn't have done it without you. Normandy, if you want to unmute and say goodbye, we'd love to say goodbye to you.
Ready? 1, 2, 3. Ready? Say goodbye.
Awesome.
Bye.
If you enjoyed today's program, please join us again. Amazing. If you are enjoying today's program, please come back. Next month, we have another one, Scientists in Action, Cambrian Explosion and Life in an Ocean, in which we will go way back in time here on Earth and talk about what life was like when the ocean covered all of Earth. So very exciting. We can't wait to see you again. Thank you so much and have a great one.